So, we are continuing with the false twist texturing, influence of process parameters. We are continuing this as we had only covered part of the effect of temperature. So, process parameters which we understood were temperature, time, twist and tension, and we did study the effect of temperature on crystallinity, crimp rigidity, tenacity and dye uptake. As far as dyeing is concerned, we were talking about a dye like a dispersed dye on a polyester, where the interactions are in a manner there which is not dependent upon the end group ionic or cationic nature. It basically dependent on how much amorphous content is there, and that is what we believe happens during texturing, the changes in the crystalline content and the amorphous content. And so, does it have any influence? This is what we wanted to learn, and after some discussion we came to a state where we said the dye uptake initially decreases because the crystallinity is increasing and the dye can go only in the amorphous region, but thereafter it again starts increasing, and we left it at this point, saying that maybe you would like to say something on it. Anybody would like to say something on this?
So, due to recrystallization, the more free space will be created. So, the dye uptake will increase after certain temperature, around after 180 degree, or you can say after 160 to 180 degree.
So, you are saying that the recrystallization is taking place because of that. The whole thing is recrystallization, that is why the temperature, dye uptake is going down. Because if there is more crystal formation, amorphous content goes down. So, why would it start increasing?
Smaller crystal became bigger.
All right. So, this is one interesting thing, is that after a certain temperature, the crystallinity may not increase too much, but smaller crystals can coalesce and become larger crystals. So, there is a concept of amorphous volume per unit crystal. And if for whatever reason is not the total amorphous content, but the amorphous content associated per crystal, if that increases, then there is a possibility that the dye may diffuse more. And so, something like this one can assume. So, there is a fiber. In this fiber, you have smaller crystals of various types, let us say arranged in any manner. A large number of small crystals oriented or disoriented in a fiber depends on what is the percentage, and the dye has to go inside the fiber, and we understand that you would not see any dye inside the crystal structure. So, if you have large number of such smaller crystals, then they do offer some resistance to motion and diffusion. If in the same thing it changes that crystals become less in number and larger in size. Just then you have more opportunity for dye to diffuse in, having less tortuous path, and so one sees that the dye uptake actually starts increasing because crystal percent is not increasing so much, but the rearrangement is happening. Now, this curve which we were looking at, how is it important to us? If this curve is true, then how is it important to anybody who is texturizing? Whenever we do any texturizing, we optimize the temperature, in this case for that matter, there is going to be a variation. You set it up at 200 degrees centigrade, you will have 200 plus or minus some degrees. Now, it depends on how much accuracy that you have. Is it a 0.1, is it a 1 or is it 2? So, based on that, at any given point of time, as the fiber or yarn is moving in the texturizing machine, sometimes it may be actually having a temperature higher than the average, sometimes it may be having lower than the average. And if the dye uptake of this material depends on the morphology, whether larger crystals are present, smaller number of larger crystals or larger number of smaller crystals are present, or crystallinity is less or crystallinity is more, then when you finally dye the textured yarn, the yarn or that part of the yarn is going to take different amount of dye at equilibrium. Even whatever temperature that you have fixed, the parameter that you have fixed for dyeing. So, it does not matter so much, but the moment you make a fabric out of it, so depending upon which type of yarn and which portion of the yarn is coming near the other portion, you can start seeing variations in which people refer to as barre. So, as a customer you would like to reject, this does not look good, you wanted a uniform dyeing and the textured yarn is not uniformly dyed. And so, somebody who is optimizing the temperature, the first parameter that you were looking at was the crimp rigidity, because you are preparing a textured yarn, and suddenly find no, there may be something else also you must look at it, and which is not tensile strength or abrasion resistance. You want to look at something. If somebody says, if you have to set up your machine temperature, suppose this is the curve may be different for different fibers with different histories, that is okay, but you will get a dip. What temperature, the machine temperature, would you like to fix? A temperature which could be somewhere here, a temperature to be optimized here, a temperature to be optimized here. Yes? Flat region. So, now you suddenly have another reason for you to do optimization, because if you are in the flat region, if some variation occurs in temperature and also whatever is happening as far as the dye uptake is concerned, which is visible thing, is going to be less compared to a situation here where the same variation in temperature can give you variation in dye uptake of this type, right, this much variation in dye uptake, which will be more visible. And after all, people reject things on the first look. If you can just see from your eyes and say there is a defect, then you are not going to buy. So, a texturizer should not be bothered only about the crimp rigidity and tenacity and whatsoever, or crystallinity, which of course most people do not even know how to see it from eyes. This can be more dangerous. So, that is what we thought will be important. So, the next parameter is the time of texturing. So, we had temperature, the next parameter which you can optimize by changing the machine speed. If you can change the machine speed, the time of texturing can be changed, because the length of the heater is going to be constant for that machine. You can have a different machine with a different length of heater, but as far as one single machine is concerned, this is what will be available to you. Remember again that the boundary conditions remain the same thing. We are all talking about fully drawn thermoplastic multifilament yarns, twist texturing, single heater. So, that does not change, because all understanding is to be within this constraint. So, time of texturing can be now talked about as either a heating time or a cooling time. So, that is why we said in a texturing machine you have a heater, and then after the heater there is a cooling zone before you do detwisting. So, what is happening? During heating, as required, a bond breaking is taking place. That is, you have intermolecular bond breaking, so that you get more freedom, which could be, as you said, partial melting or recrystallization. And then we have rearrangement of molecular chains in the energetically favorable configuration. So, either they would crystallize or they may disorient, both are energetically favorable. So, this is what will happen. So, during heating, as we can now recall, the bond breaking and rearrangement will take place, all right. So, crystallization can take place during the heating itself, and cooling is the time where you are interested that the new configuration which have been achieved gets frozen as soon as possible, and therefore, you want to get to the temperatures which are lower than glass transient temperature, so that no further change occurs. So, that is kind of a permanency, relative permanency that you want to achieve. Now, this is an interesting question which somebody would like to always know. Time temperature superposition, what it means in a process environment is that if I am working at a higher temperature, I can reduce the time, or I can work at a lower temperature and increase the time. So, from that point of view, whether this type of superposition is possible in what we are considering as a textile fiber, right. The textile fiber has crystalline amorphous region that we now understand. If a material is totally amorphous and has no chance to crystallize, in such situation the time temperature superposition is absolutely possible. But if you have a crystalline region, so we understand during this process there is one minimum and then other minimum, and you have to go from one minimum to another minimum for a setting operation. And what therefore it means also is that you have got to supply certain amount of energy before anything can take place. So, suppose tomorrow you decide that I like to do texturing at room temperature, leave it for 1 month after twisting and come back and see the effect. You may not see anything unless and until you give enough energy to overcome this barrier. If you can overcome this barrier, then it is spontaneous. If you are operating in this zone, then maybe yes, time temperature superposition will be possible, but not every time. So, you got to be in a range, and therefore, this optimization is okay, that if you are in the range of, let us say, in a polyester from 190 to 210, well, you can play reduce temperature, increase time, etc., but not in a large range, where you will say that partial melting is not taking place, is not complete. So, how will the rearrangement take place? So, in the textile material, which are useful textile material, which have crystalline and amorphous regions, this time temperature superposition will not be possible in the standard method sense. So, we know that the yarn is at room temperature when it enters the machine. So, when will the bond breaking take place? The bond breaking can take place only if the yarn has achieved a certain temperature. So, the time of texturing would have to account for that time as well, which is taken to raise the temperature of the yarn from from the room temperature to a certain temperature, after which all these things. So, the time required even to raise the temperature is going to be interesting. What kind of a curve we are going to get here? Let us say this is the room temperature. The yarn temperature will start rising, and at best it can be equal to heater temperature. And suppose this is equal to heater temperature, and somewhere down the line here the bond breaking may also start, rearrangement may also start, and the optimization can be that yarn temperature is equal to heater temperature, and therefore, we say there is no point. No, there is a point. You may actually give more time than this also, because you are not interested in raising the temperature, you are also interested in bond breaking and rearrangement. Therefore, the heating time would be also time required to take it to a certain temperature, and this will also depend on what? The dimension of the yarn also. If it is very fine yarn, fine denier, then the time taken may be different. And so, this is dependent on the yarn characteristics, which may be specific heat, which may be the overall denier, and of course, that all is, the first part is something to do with the chemistry, the second part has something to do with the dimensions of the material itself. So, one will be, we are of course, as we said, we are doing a contact heating, the machine that you have seen. And so, should be most efficient way of heating. You could have done non-contact heating also, but that is in your control when you design the machine. But after that, it is the material, how it responds. This question was important in a sense that, let us say, we have a machine which has a heater length of 1 meter, which is the primary heater we are talking about, and you want to run the machine at 300 meters per minute. All right. So, how much time the yarn is likely to spend in the heater? So, 1 meter heater, 300 meter per minute. So, how much time is likely to spend? 20 seconds. I am just keep writing. Anyone else? Any other figure?
0.2 seconds.
All right. So, this is not there. 0.2 seconds. You understand this time? 1 second itself is considered a small. Now, you are only looking at a machine which you want to run at 300 meters. The modern machines may be running at 1000 meters or more. How much time are you giving in the heater? Look at the expectations. The expectation is that from room temperature, the yarn will attain a right temperature, and also within this time all rearrangements will also take place, and this is what happens also. That means your material responds, but you have to be as efficient as possible as far as the transfer of heat is concerned, energy transfer. But this was not to check your calculation. This is, or this is to get an appreciation as to this is the smallest, so much less time that you have, and you are supposed to optimize this. So, we would be obviously interested in learning as to what happens when you increase the heating time. I am writing heating time because we have something called cooling time as well on crimp rigidity. What do you think? Let us have some guesses. Heating time and crimp rigidity. So, what do we think will be the thing? What kind of a curve are we looking at? If time is very low, what do you expect? High crimpacity, low crimpacity? You must know what you expect to happen during this time. Any guesses? It will increase then decrease. All right. Any other thing? Any other thing that you want? The time is required to raise the temperature of the yarn, allow bond breaking, and rearrangement means either crystallization, disorientation, what have you. So, all right. Let us say this is okay. Why does it increase from here to here, crimp rigidity? Why? Why does it increase? Is it it should increase because you are allowing time for breaking of intermolecular forces and rearrangement. The more time is allowed, the more of this can happen, and therefore more, we can say, the energy level, the free energy is going down, is getting into the more stable state. More stable state means more set, and that means a better crimp rigidity, right. Why does it go down then? It should keep increasing, or could have become constant when there is no scope for further improvement in, let us say, crystallization. Why does it decrease?
Melting of crystals, and after that sudden cooling. So maybe
No, this is heating time. We not gone to the cooling part as yet. And you can appreciate that we are saying that we have already probably optimized temperature, and we are working at a temperature which has been optimized, okay, the constant temperature. So, now the temperature of texturing is constant, only the time is varying. So, have you ever kept any material which is called a polymer fiber in an oven for a longer period of time? Have you ever seen what would happen? You never had got a chance to say any material in an oven or a hot environment kept for a long period of time? If you see, it becomes yellow, start becoming yellow. If any material which was approximately white starts turning towards yellow, you can appreciate that there is some degradation starting. something which was white is becoming yellowish. That means certain types of groups which can absorb something from the visible radiation have start growing, and you start looking at something which is different. So, you can keep anything for a long period of time at a temperature which is which the material is susceptible, then you will start seeing degradation. So, in the temperature case also we were looking at a degradation after a certain time. In the time case also we will be looking at a degradation starting, although this rate of degradation will be slower compared to the rise in compared to the behavior that we saw when we look at the temperature increase, because here temperature is constant. So, time has an effect, that is not something will not happen. So, it has a positive effect as well as negative effect, and therefore, although you may be lucky that you say, well, this is my time, but if you go beyond this, you can get some degradation also, which would mean result in loss of crimpacity as well. So, you obviously have reason to optimize, you do not go beyond, and who wants to increase the time? If you increase the time means machine speed is slower, you want more production. So, you actually have a tendency to go for the faster speed rather than the slower speed, but when you are doing a research you do obviously something like that as well. So, what will be the effect of heating time on tensile property like tenacity? So, remember, because we are setting a twisted yarn and therefore, the orientation of the yarn is going to go down. So, when you test any of these properties, it will only go down. Now, the question that remains is it so important that you should worry? Well, depends what are you doing with it. Generally during use, because you will be in a stretch zone rather than in a real extension zone. So, some losses may not matter. So, you can expect some losses will always be there, because texturing is basically a disorientating process. So, tenacity will go down. If it goes down by 10 to 15%, nobody bothers. If you do something wrong and goes down below 50%, then somebody will say, what are you doing? And it is quite possible the fiber may not actually look white, in case you are doing a white, using a white textured yarn. Come to the cooling time, and what did you expect? We were expecting that during this cooling, the new configuration, which probably is at the lowest energy levels, is going to be stabilized. So, this is important in some ways. Suppose this is your room temperature and you want to measure the temperature of the yarn. What kind of a curve will be? What type of curve we are expecting? So, it will come down. This is, let us say, the temperature of the yarn as it exits, then it will keep coming down, and after room temperature, obviously there is no reason why it should go down, because that is the room temperature, no further loss. Now, both these times can be also important, because they should have a role to play in determining what kind of a final property you are getting, particularly the texturing also. Let us say we want to say the crimp rigidity in the cooling time. What kind of a curve are we expecting in the cooling time? And let us say we are still interested in crimp rigidity. What do we expect? Starting with no cooling time, 0 cooling time, and we increase the cooling time. Difficult question. Any guess? Increase like this? No?
Increase and then constant.
Like this? Right? Will it go down? If you keep increasing the time? Is there any reason? It should not go down, because no degradation can take place if you keep a material at a low temperature for a longer period, because that's how the materials are stable and we are quite happy to use them year after year. If so, cooling time is important, but if you keep increasing the time, there will be no further improvement in the crimp rigidity. So, the problem that remains always therefore is, can we change the cooling time and the heating time independent of each other? That is, I increase heating time, reduce cooling time. Can we do that? At least not in the same machine. If you know the line diagram, that if you remember, I mean the machine speed, if it is increased, both of them going to reduce, or vice versa. And therefore, people talk about texturing time, and generally they say, well, heating time, and so obviously cooling time will either go up or down. And therefore, people talk about heating length versus cooling length. Now, this is something to do with the machine, but how will you decide? Let us say I have to texturize two fibers of same denier, one is nylon, the other is polyester. The crystallinity of polyester is around, we said, 27%, 28% of a fully drawn yarn. Vis-a-vis the nylon would be having about 35 to 37%. Now, what will be the effect of this on the heating? Effect of this on the heating time? Which will require more heating? Right. So, nylon would require more heating compared to polyester. So, irrespective of whatever you do, so it will require less. So, you can say, well, I can reduce the heating length, or I can increase the machine speed. All right. The cooling length actually is, if you are, what are you doing? The yarn is at a certain temperature, it has to cool down, and this rate of cooling will depend on the temperature difference and also the property of the material. If the conductivity of a fiber is poor, thermal conductivity, then it will take more time to cool down. And so, it was understood that the thermal conductivity of polyester is poorer compared to nylon, which means polyester will require higher time compared to nylon. So, if somebody said a thumb rule, the cooling time for polyester, cooling length, let us say, the cooling length of for a polyester fiber yarn is about 2/3 that of the heating length. Two-thirds of heating length. So, cooling length is 2/3 of heating length, while in the case of nylon, this is for let us say polyester. For nylon, it is 1/3 of the heating length. If suppose you have a machine which is designed for polyester, which is 2/3 is the cooling length, Will it harm if you texturize nylon there? Will it harm? It will not, because if you increase the cooling length, there is no deterioration going to take place. The same machine therefore can be used. You do not really have to make a machine for polyester and a machine for nylon and a machine for polypropylene. Thermal conductivity of polypropylene also is very poor, all right. And the crystallinity of a fully drawn polypropylene, we are talking about polypropylene, the polypropylene thermal conductivity is also poor, and the crystallinity of a fully drawn polypropylene is also very high. So, you now have a material which requires high heating time and also high cooling time, right. So, three different kinds of classes of material requiring different kind of things. So, what will machinery manufacturer do? He will just make a machine and you say, well, does not matter, at least cooling time should be sufficient. But if it is insufficient in any case, then you are going to get a bad result. The next parameter that we have is twist. So, when we talk about twist, you can assume that we have already said that this is the speed at which we are running the machine, the time is fixed, the temperature is fixed, and now we see what is the effect of twist. When you look at any textile yarn, let us say spun yarn, you say there is some nominal twist we have inserted for whatever purpose may be to hold the fibers together. So, what do you mean by this, a normal twist or a nominal twist? What it means is that if you take the fiber or a yarn and bring the two ends together, it will make a loop, all right. This will be normal twist. If you have more than the normal twist, then you should expect snarling, right. There is more than normal twist. So, the yarn, whenever given a chance, that you bring two ends together and start snarling. So, in a normal textile processes, we are not interested in snarling to take place, right. But in the texturing, our twist levels are very high, much higher than this level that we are talking about. And this is a thumb rule, you know, if this is the final rule, then life will be very different. It is a thumb rule, that depending upon the denier of the yarn, the twist can be decided, and around this value you will optimize, because your heater may be different, your number of fibers may be different, whatever. It is talking about total denier only. Okay. Now, what it approximately says is, approximately, that irrespective of whichever denier you use, the helix angle, at least on the surface, the helix angle is approximately going to be same, approximately, where the optimum is going to be coming, or around which you are going to be doing the experiments. So, this is what says, empirical formula, a thumb rule, right. So, higher is the denier, lower will be the twist required, and vice versa, but it is quite high. So, just to get a feel, this false twist texturing obviously has a twister other than everything else, right. So, you have the same line diagram, you have a feed roller, you have a heating like a primary heater, we are talking about cooling zone. So, we talked about heating, cooling zone and temperature, and now we have a twister. Now, you just want to, I want you to appreciate something, okay, what is a twister and how does it happen. There is something called a pin twister. A pin twister obviously looks like a pin. But this is hollow, all right. And this bulb is also hollow. So, there is a tube and there is a bulb, and here somewhere there is a pin. So, what happens is, if suppose you have the yarn which is, let us say, going inside the tube, it is taken one round here and comes out. Now, if you give one twist to this, we are expecting one twist in the yarn. This is called positive twisting. If you give one twist to this spindle, then one twist is inserted in the yarn, which could be false twist, on one end S, the other end Z. So, this is something called a pin twister, and the pin is rotated on a support which is magnetic support, or there is a support in which it is there. We will talk about it when we come to that. But my main interest is that there is a spindle which is going to be rotating, and inside the spindle there is a pin, and one rotation of a spindle means one rotation of the yarn, one twist in the yarn, and so that is it. So, the twist that we are talking about. If machines which use this type of twisters will be called pin texturizing machines, all right. So, the pin is only here, rest is spindle. It is a very interesting piece because hollow, then you have to design everything else. So, let us do some little check and calculations. Okay. Calculate the required RPM of this spindle that you have seen just above. If the denier of the yarn to be texturized is 100, okay, you know the ballpark way to calculate the twist. So, what will be the RPM? So, there is some little calculation required. I like you to do whatever you can do to give me some answer. Required RPM of the spindle. Now, you understand RPM of spindle will also be equal to the twist that you insert. So, that is the correlation, that is part of it. And based on the denier, which is now 100 given to you, and the speed is the same as 300 meters per minute you want to run the machine. So, would you like to do some quick calculation? You can use whatever you want to use to give me some value of the RPM at which the spindle is supposed to be rotated. So, speed remains the same, 300 meters, the yarn to be textured is 100 denier total, and we need RPM. So, are you doing some calculations here? How much? Any value that you want to give me, please give me. 21,300. Just give me the number, I will just keep writing and we will then decide right or wrong. What is the number first? 20,300 RPM, right? 21, all right, 21. Any other number? Any other number somebody is getting? You are using calculator, I believe. Yes?
838, 533.
Can you just again give me the number?
838,
838
581.
581. 838
582.
and there is one more, so it's okay. Approximately. So, how much is this approximately coming? Look at this. So, this one definitely is little away. The question that remains is, at what speed? Again, it is not to test your skills. Please find out exact values whenever you want to find the value, which will be required whenever we want it in examination. But at what RPM you want to run this machine? You appreciate that? Which spinning machine or any other machine is running at this RPM in textiles? Is there any machine? Any part of the machine that is running at this RPM? Right? So, interesting, isn't it? So, this is the kind of value that you are looking at, 10 raised to 5 times. Now, you change the speed of the machine to 600, So, it is not the time you are reducing, you are also wanting the spindle to rotate that fast. All right. So, what do you think would happen if we increase the twist in the yarn? We know whatever twist now it means, we know what levels are we talking about. If we increase the twist in the yarn, let us say twist per meter or whatever, at least twist in the yarn, what will happen to the crimp rigidity? It will increase. We go back again, do some exercise. We are now looking at twist and crimp rigidity. It will increase. Increase in which way? Level off? All keep increasing. What will happen? Level off? So, level off. So, first question is, why would crimp rigidity increase? Time temperature is constant. One of the reason could be because the number of helices per unit length are increasing and is like a spring, for example. Then obviously, the resistance offered will also be more if number of helices per unit length are more. That is what the twist is going to do. But when we keep increasing the twist, why it is leveling off? Time that we just stop here and think. Okay. So, the number of helices per unit length are not going to decrease if you keep increasing the twist. So, we have not concluded this part, but we will like to talk about it when we meet again. Thank you.